This video is the first in a series on portfolio optimization. All of our portfolio optimization work will be based on combining different stocks and possibly other assets to find the best return we can get while getting the lowest return possible. And so it's all going to be about returns. Throughout this video series, I'll color code the returns in this yellow background just so we can all see clearly where we're seeing the returns. We can calculate returns two different ways. We typically in this class do the discrete return, which is just simply the percentage change from one period to the next. We could alternatively use the natural log of the current period over the previous period, and that lends a lot of flexibility when converting among periods, but we won't go into that here. We'll keep with a straightforward discrete calculation. Everything else would flow through just the same if we used a different way to calculate the return. And for this series, I'm going to include the formulas up in the comments section so that we can copy that, quickly paste it into a cell, and then you can just double click on the label. So if I'm looking for the current price, I know that's here. If I'm looking for the previous price, that's here. Then now we've calculated the discrete return for that period. So Kellogg stock lost about 31% over the calendar year 1998. And we can copy that formula and see what both stocks did, Kellogg and ExxonMobil, over about a 18-year period there. If we'd like to know what the return is likely to be going forward, our best guess for expected return is the average of historical returns. If we'd like to know what the standard deviation of returns, or how much risk there is, how wide the spread is and the possible outcomes, again we'd use the standard deviation. And I'm using stde.p to indicate the population standard deviation. It would be more pure to use the sample standard deviation here because this is only a sample of the possible outcomes. But the matrix math that we'll use later will flow much better using the matchup with the population standard deviation. The difference is insignificant in our work, and the uncertainty in this approach is much greater than the difference in those mathematical approaches. Now, all of these returns can be thought of as a percentage return, and so therefore the expected can also be. And the standard deviation of returns can also be thought of as a percentage. So I'm going to go ahead and format those this way. If we copy that across to ExxonMobil, then we see what we would expect is that the ExxonMobil stock with a higher expected return than Kellogg also has a higher risk than Kellogg, because investors typically demand a higher return if they're going to take on a higher risk. We'll create a plot that we'll call the risk return plot and show that. Notice the symbols I use for expected return and standard deviation. If I try to type expected return into Excel like this, it outsmarts me and thinks that I wanted a symbol there. So my trick to outsmart Excel is capital E, open parentheses, R, space, parentheses, and then before I hit return, left arrow, hit F2, left arrow to delete that space, and then it won't put the symbol in. And then to get the Greek letter sigma, we can go to data, insert, symbol, choose Greek and Coptic, and then scroll down within the Greek letters until you find sigma, and you can insert that. And that's how I get those symbols. Next, we will find what the expected return and risk would be for a combination of these two stocks.